take our formula and plug in time, right? What am I going to plug into this? Not 2023, right? I'm going to plug in how many years it's been. So how many years since 1986? 37 years? 37 years. So I want to know what A of 37 is. A of 37. And that'll equal 10 e to the negative 0.023105 times 37. And that, you just try and type that all into your calculator at one time. So 10, 0.023105 times 4.25? 4.25. 4.25 what? Pounds. So roughly about half of it has gone away. And in another 37 years, or another 30 years from now, there will still be half of that there. And 30 years after that, half of that, right? So if 10 pounds of it causes you to evacuate a city, right? 4.5 pounds will also make, people are still not going to go there, right? So nobody's going to be going there anytime soon. Now, 30 years, that half-life seems kind of long, yeah? So what are some of the other radioactive material half-lives? Half-lives. So when you have nuclear weapons and you have, so you all know the world's been crazy, right, lately? So one of the threats is nuclear war, right? So the bombs themselves would probably, if there was like an all-out nuclear war, right? The bombs themselves would take out a lot of people, right? And in San Antonio, military city, right? We've got several military bases here. We would be on the list, right? Targeted for sure. Not to be doom and gloom, sorry. But it's true, right? It's true. We have Lackland, we have what is it, Brooks? Randolph? I mean, right? So we are on the hit list, right? So for a lot of people in San Antonio, it would be the initial blast. But for people in the outskirts, away from San Antonio, right? What is it that actually gets you? Radiation. The radiation, right? All this radioactive material goes into the clouds, into the sky, and then the winds carry them, and then it rains, and then it gets into your soil, and then it gets into the water, and then it gets into your skin, and right? And it basically, radioactive material, it's like a microwave. Think of a microwave, right? You put food in the microwave, comes out hot. Radioactive material is basically like microwaves, but what it does, it doesn't cook you and burn you. It actually just goes in there and alters your DNA. So it fries your DNA, and then your cells in your body don't know what to do anymore. And so yeah, it become huge. Then you basically, your body doesn't function anymore. So things start to break down. This is fun, huh? This is fun. So this radioactive material, right? And then also what happens? It blacks out the sky, right? And you black out the sky, there's no sunlight, the trees, plants die, animals die, there's no food, right? So yeah, it's like, that's why they call it mutually assured destruction, right? If you have this huge nuclear war, you're assuring basically the end of humanity. There will be some people who survive, but it'll be a different world, right? So, okay, so why am I talking about this? What is the half-life, right? Some things like caesium-137, 30 years, right? Some of them 8 days, But there are some nuclear materials that have half-lives that are thousands of years. So there's no way to get rid of radioactive material easily. You can't just it's not like a fire. You pour water on it, it goes away. So do y'all know what we do with all of our radioactive material? Do y'all know what we do with it? All the waste, you know? Where is it? Not in the ocean. Underground. We stick it in mountains. So we drill big holes in mountains, and we shove all the radioactive material in there. And we say, okay, good. Like that. That's what we do, right? And there's a lot of radioactive material. It's not just the radioactive material, it's anything that came in contact with it. So nuclear reactors, they use water to cool the reactors. That water now becomes some soupy mess, right? We have to contain all of that. It has to go somewhere. So there was, I'm going off topic, sorry, but this is interesting to me. So back in the Bush era, Bush 1, the first president, Bush, George Bush, the first president we had, during his reign, he was part of a plan that we had to, basically we had all these big concrete holding tanks. And inside these holding tanks were a bunch of this is like nuclear soup, all this stuff, right? And they did a special, it was on TV, where they said if you took like 1 cup of that soup, and like if I had placed it in the center of this room, right, didn't tell y'all about it, like we'd all be dead within like 3 weeks. Like that's how bad it is. It's just 1 cup of it sitting in here, right? We had these huge concrete, containers full of this soup. And the problem with soup is that if it spills, well, how do you contain it, right? Right? So there was this plan to take this soup and send it through this factory, and it would go in as liquid, and it would come out as solid. Okay, so they would convert the liquid to a solid, and then they would put it on trains and go ship it to the mountain, shove it in the mountain, be done, right? So that was the plan. But there was a problem. They started doing this, and in this procedure of going from liquid to gas, to solid, they were creating fumes, and the fumes were bad. So they couldn't really get this done. And so these concrete things, holding tanks, do what concrete does over time, right? Which is crack, right? These things start to deteriorate. You can't keep it in here forever. So what do you do, right? What do you do? This is a problem we have. We have a lot of problems, climate and all that stuff, but this is a problem we've created for ourselves, right? And this has never worried me as much as the fact that we have all of this waste as a result of what? The Cold War. You all know what the Cold War was? It was basically the Soviet Union, which is now Russia, and the United States, just basically pointing all of our weapons at each other, saying, yeah, go for it, Go for it. It was just a big pissing contest, really. And so, we were sitting there and we had all these byproducts, all this nuclear waste, all this material. The United States has been somewhat responsible in the sense of keeping it, clean and, trying to contain it. But Soviet Union has fallen apart, right? Like it fell apart many years ago, and now it's broken up. That's why there's this war in Ukraine. Ukraine used to be part of the Soviet Union. And now Russia wants it back, right? They want part of it back. So this whole thing that's going on, what did Russia do? What did the Soviet Union do with all their soup? Where's their soup, right? Where is it? Who's regulating that? Are they putting it in mountains? So again, I've seen reports where people have driven in the countryside in the Soviet Union or Russia with those, they have meters to measure radioactive. It's like, I think it's called a Geiger meter or something. You go and it starts making a sound, and I've seen videos of people on the countryside on a dirt road with these tongs, with a suit, a hazmat suit on, picking up shit off the ground that's radioactive and putting it into a container, and it's just in the middle of the countryside. I've seen this on, back in, I don't remember when I saw these videos, but it's not like a YouTube video I saw last week. It's decades old videos, and that's always concerned me. It's where's all their stuff? And what's the big point of all that conversation? Well, it's not going away, right? It's not going away. It's not just going to kind of fizzle out. It's going to be there. It's going to be there for generations after generations, and still going to be dangerous, and so, but mathematically we can show, right? We can show how long it's going to be dangerous for, right? All right, that's fun. How are we doing on time? Are we ready to move on to the next topic? We got a little bit more time here. Here's what I'm going to do. Example 3 on here. I would like for you to do that for homework. It's just for your own, okay? Example 3, so it's the back of the first page. Estimate the age of ancient tools. I'll read through the problem. Traces of burned wood along with ancient stone tools in an archaeological dig in Chile were found to contain 1.67% of the original amount of carbon-14. The half-life of carbon-14 is 5,730 years. Approximately when was the tree cut and burned? So all living things contain something called carbon-14. And our bodies, or if it's a tree, or if it's, you know, any plant, any animal, any living thing, creates this carbon-14. As long as you're alive, your body is continually holding a certain level of carbon-14. As soon as you die, then your body is no longer able to generate the carbon-14, and the carbon-14 starts to decay. And so if you find a bone or a tree, a piece of wood, an old piece of paper, anything, you can measure the carbon-14 in it, and from that, you can use its half-life to figure out when it died, right? So if it's a person, you could try and estimate when they died. Now, it's not going to be accurate to like the minute, but it can give you, like, you know, some roundabout idea. And this is how we date things. It's how we, you know, oh, we found a bone. It's 40,000 years old. Well, how? Carbon-14. So I want you to try that yourself, okay? Now, the next thing, and this will be the last thing for today, we're going to do Newton's law of cooling. So this is actually a really, really interesting formula to me, I think. So if you go, like, this is kind of a morbid class. Sorry, I don't mean it to be, but it kind of is turning into it. Newton's law of cooling works like this, right? So let's say that someone calls the police. They're like, hey, you know, I haven't heard from my friend. Can you go do a welfare check? They go knock on the door, door's open, they walk in, right? They find a body on the ground, right? Right? You've got this person who's dead in this room, okay? One of the first things that the detectives will do, right, is they will measure the temperature in the room. So like in here, the temperature according to this thermostat on the wall, it says it's 68 degrees in here, 68.3 degrees, right? So they'll measure the room temperature. And then they'll go take the temperature of the body. Now, what is our temperature normal? Normal human temperature is what, 98.6 or 7 or somewhere around there? So if that body is 93 degrees, then what can that tell you? It's pretty recent, right? Now, if the body is the temperature of the room, then it's been there for a while, right? Now, if it's what if it's 68 degrees in here, but the body is 72 degrees? Well, then it's been a little longer, right? Newton's law of cooling allows us to actually figure out pretty accurately how long that body would have been there, because what it can do is it can measure how much time it takes for some body to reach the temperature of the surrounding medium. So if the room's 68 and I put something in here that's 100 degrees, Newton's law of cooling will tell me how long it's going to take that thing to get down to the room temperature. Make sense? Yeah? So let's see the formula. The formula looks weird, but it's just a formula. So here we go. It's U of T. It's named after Newton, Isaac Newton, who's also the father of calculus. One of the fathers. There's two, but that's not important. He contributed to this, coming up with this formula. So here's the formula. U of T equals T plus, in parentheses, U naught minus T times, this is multiplication, times e to the kt. And here they're saying, for this, K is always less than 0. Now, look, this is not uninhibited growth. Okay, this is a completely different formula, completely different topic. We're talking about Newton's law of cooling. So let's talk about what each thing is here. The T is the temp of the surroundings, right? I'm just going to put the medium. When I say the temp of the medium, that would be the temperature of the room or the temperature of the, outside, whatever it is, right? Now that you would have to assume that that's actually being held constant, right? Like this room is being held at that constant temperature. So that's your capital T. U naught is the initial temperature of the heated object. And let's see here, K is a negative constant. And that's it, right? Now, what does U of T give you? What do you think? What does, oh, and T here is time, sorry, T is time. And U of T, what is U of T? You don't have any guesses? If capital T is the temperature of the surroundings, U sub 0 is the initial temperature of, let's say, the body on the ground, right? K is some constant, T is time, U of T would be the temperature of the what? Object? Object at time T.
Is it always negative because it's always decreasing, right?
Yes. Mm-hmm. Yeah, it's important because it says it on here. Newton's law of cooling states that the temperature of a heated object decreases exponentially over time toward the temperature of the surrounding medium. All right, so the object is cooling off, right? Not heating up. Because, right, if I put an ice cube in here, right, then the ice cube's going to try and reach the temperature in here. So that's the opposite, isn't it? That would be, and that's not necessarily this formula, all right? Okay, so now there's an example here, but I feel like we should do our own. Do y'all want to do that detective work on that body we find? Yes? Okay, so let's say that we're detectives, right? We get a call and we find a body, right? Do I need to write this down? We find a body, right? It's 68.3 degrees in the room, okay? This is our room temperature. And then the body we find, we take its temperature. And what do y'all want the temperature to be? If it's 68.3, this isn't going to work, right? Because now it's cooled off to the surrounding, and then it could have been there for a week. You don't know, a week, 10 days. You don't have any information. You need it to be a little bit higher for this to work, right? So what do y'all say? You want to go with like 72 degrees? 72.5 degrees. 72.5 degrees. All right, so we go in here. We measure temperature at 68.3 in the room. We measure the temperature of the body. It is 72.5. Okay, let's just see. Do we have anything here right now in our formula? Do we have anything? So can I, U of T, I can write is, capital T, right, is 68.3 plus parenthesis, let's see, minus 68.3, and then e to the kt. Do y'all agree with that much so far? I'm going to put U naught here. Do y'all agree with that? Just the fact that it's 68 degrees in the room? Okay, is there anything else I can plug in here?
We know the body 98.6, right?
Pardon me?
We know the body's 98.6.
Okay, so what we are going to assume is that this person didn't have some crazy fever, right, when they died, that they had the average human body temperature, which would be what? Our initial temperature of our heated object, right? The initial temperature of that person, which would be, let's go 98.6. Okay, 98.6. So we can fill that in now, right? This we're going to fill in. So U of t equals 68.3 plus 98.6 minus 68.3 e to the kt. All right, what is that? Subtract that, what do we got? 68.3 plus, what's that? 30.3? Yeah, 30.3. E to the kt. What do you think I'm going after here? What do you think I'm trying to find right now? I'm trying to find K. I'm trying to figure out if I can figure out this rate. Now, what do we know at time 0? At time 0 was when the person actually died. That would be when the clock starts. And you can check it. If t is 0, what happens? If this is 0, you get e to the 0 is 1. And what's 68.3 plus 30.3? 98.6. So at time is 0, the temperature of the body is 98.6, right? But that doesn't help us with K, does it? So we're the detectives. What are we going to do? We need to figure out what K is.
We need T first. We need to find T first.
So, yeah, don't we want to know when the temperature of the object at time t, don't we want to put 68.3 right here? We want to know when the body, right, reached the temperature that we found it at, right? Oh, sorry, not 68, 72.5. We want to put 72.5 here, right? And figure out what t is. But we can't. Because if I put 72.5 here, there's two things I don't know. I don't know K and I don't know T, right? I don't know two things. If I knew what K was, then what I could do is just put 72.5 here and then solve for T. So I need K. So the detectives sit there and what do? It's something very clever. We found the body, right? And we measured the time. We measured the temperature, and it was 72.5, right? We're like, shit, how long has this body been here? What we do is we wait. We wait an hour, and we take the temperature again. Okay? So we're going to have two data points. We have the point where we found the body, right? And let's actually call that time. Well, that time we don't exactly know, right? We don't exactly know, but let me write down what we're about to do. Okay, so we wait 1 hour. We could wait 1 hour, and we take the temperature again. And let's say when we do that, we get, what do y'all want? 70.2. Okay, let's say an hour later, we take temperature, we get 70.2 degrees. all right with that? Now this part's going to be tricky, really, really tricky. Let's see how you do with this. Just remember that t equals 0, right, is when the person died. That's when the clock started, right? Then we walked in and we took the temperature, right? At some other point in time. And then we took the temperature an hour later. We got 2 different temperatures, right? 2 different temperatures at 2 different points in time. So I'm going to somehow use that right now to figure out what K is. So let me erase this. Let's let T1 be when we arrived. And then the temperature then was, what was it? 72.5, right? And then let T1 plus 1 be the hour later. And now the temperature was 70.2 degrees. You see what I'm doing? This is a subscript. T sub 1 is when we arrived. I just don't want to call it T because T is like a generic some point in time. T1 is when we got there. And we took the temperature, we got 72.5. And then we waited T1 plus 1 hour. 1 hour later, we took the temperature again, we got 70.2. I'd like to translate both of those into the formula. So using this formula right here, let's see what happens at T1. So at T1, what's happening here? Do we know the temperature of the body at T1? What is it? 72.5, right? Equals 68.3 plus 30.3 raised, E raised to the K times T1, which I don't know, right? This is going to get messy. This is a messy problem, but I think it's, because it applies to the real world, I think it's an interesting problem, worth us doing. Okay, do you all agree this is what happened when we walked in? At some time when we walked in, right, whatever it was, we took the temperature of the body and we got this. Now, an hour later, what happens? So at T1 plus 1, an hour later, what's the temperature of the body? 70.2 equals 68.3 plus 30.3 e to the k. Okay, now what's here? T1 plus 1, right? T1 plus 1. An hour after that time, we got a different result over here. Understand that? Okay, how many equations do you see here? 2. How many unknown variables do you see? 2. If you have 2 equations and 2 unknown variables, you should be able to solve for both variables. The question is how. So I need to continue with this. I have 5 minutes. It's going to be close. Let me see if I can continue. I'll need that back in a minute here. Tell me if you believe this, all right? Do you agree this line right here can be written this way? 70.2 equals 68.3 plus 30.3 e to the, all right, I'm just going to show you what I'm going to do over here. E to the k times T1 plus 1. That's the same as e to the k times e, no, let me do it this way. E to the kt plus k, yeah, like that. So if I distribute this like that, do you all agree with that? If I distribute this through, I get this. Yeah? And then isn't that the same as e to the kt1 times e to the k. What I'm doing here is I'm using properties of exponents. I'm going to show you backwards. If I did x to the n times x to the m, what do you do to these exponents? Add them, right? So this is x to the n plus m. That's exactly what I'm doing, but I'm doing it this way. I'm doing x to the n plus m is equal to x to the n times x to the m, right? And then this I got from just distributing the k through, okay? So this is e to the kt1 times e to the k. All right, just make sure you understand those two are together right there, right? I'm going to come here. Help me do some algebra here. Get your calculator out, please, somebody. This line right here, I want you to subtract 68.3 on both sides. So do 75.2. Sorry, 72.5. Subtract 68.3. What do you get? 4.2. Now it's gone, right, from here?
Yeah.
Divide by 30.3. What do you get? 0.1386 equals what's still here? E to the kt1. Okay, does everyone follow what I did there? Well, I didn't do it, thank you. Subtracting that and then dividing this. Okay, do the same thing on this one. Subtract 68, divide by 30.3. Subtract 68.3, divide by 30.3. What do you get? So 70.2, take away 68.3.
0.0627.
0.627 equals, what's still over here? E to the kt1 times e to the k. All right, do y'all see what I did? I didn't do it, but yes? Y'all follow what I'm doing? Move things around? Anyone see what I'm about to do?
Natural log.
No. That is this, isn't it? Isn't it? Isn't e to the kt1, isn't that this? And what is that value? That right there, right? I can plug that in right here to replace this whole thing. Remember, these are two different equations, right? Two different equations. So if I'm telling you in one equation that e to the k times t1 is this, and then this is equal to e to the k times t1 times that, then I can replace that with that. So I get 0.0627 equals 0.1386, right? That's that being plugged in, and then e to the k. I'm going to run out of time. What do you think now? Divide? So take your 0.0627, divide by